Battery maybe. It's a battery. Have to press the button, huh? Have to press the button on it. Technology.
Alrighty, so next up we have Wagner, who did her thesis underneath Dr. B.
Well, today I'm going to be talking to you about developing a sensory behavioral assay for the zebrafish autism model. So, autism spectrum disorder, ASD, is displayed in individuals of all ages. Most people are getting diagnosed by the age of 2 due to new eye tracking technology, but they display a lot of different behaviors even at age of 3 months old. So they lack the eye contact, and they lack showing interest in different games and toys that normal infants would show. 1 in 68 children are now being diagnosed with ASD in the United States, which is kind of a huge number. So many speculate what causes ASD, why is it happening? Well, there has been a lot of theories about vaccines, GMOs, age of the parent, and substance abuse, but nothing has been proven yet, and nothing has been determined. And once again, with everyone at this age, there's a lot of different characteristics, but they also share a lot of characteristics. ASD is now an umbrella term for many different disorders, but the main ones are Rett syndrome, autism, and Asperger's syndrome. And as you can see in this picture, there are key characteristics that you can see with individuals with ASD. So for instance, you can see the folding around the eyes, a almond-shaped head, a wider forehead, and a smaller midface, as well as a thin upper lip, a flat nasal bridge, and a upturned nose. And those are the key characteristics that go along with it. Not all of them will share those, but that's what you will see the most. There are 3 different levels of ASD. High-functioning autism is what you will see most in your surroundings, and that is because they can interact with other individuals, but they still need a lot of support from a parent or guardian so that you can function normally. Whereas the level 2 autism needs a lot of support. They cannot function normally in an interaction, but they can still try to interact, but which is completely different from level 3, which is a severe autism, which cannot interact without a parent or guardian present at all. This really impairs their day-to-day life. So today we're going to talk about 3 main stimulus, and we're going to look at the behavioral phenotypes that go along with it. The main stimulus that we're going to look at is social, olfactory, and tactile. So in response to social at 3 months of age, you can see a lack of eye contact, lack of interest, and then you see the tactile stimulus response, where they don't like to be cuddled or held. And then the olfactory stimulus, where they get very overwhelmed if they experience a new smell or a new taste, which will cause a lot of meltdowns. As you can see also, the behavioral deficiencies in school-aged children, they show very similar ones where they lack the eye contact, they lack appropriate interest in other individuals, and they have difficulty following instructions. Okay, this is a video of what high-functioning autism looks like.
It's almost deafening.
Example of a tactile stimulus response.
Imagine not being able to read the facial expressions of others, and as a result, you have no idea what they may be thinking or feeling.
An example of a social social response.
Imagine that someone is trying to talk to you in a noisy store, but you cannot focus on what that person is saying because all the voices blend together.
Example, the tactile slash social.
Imagine taking a shower, but the water hurts. In
Example,
fact,
another
it feels
tactile.
like getting caught in a hailstorm.
So many of you are probably wondering, why are all these different behaviors happening to so many different stimulus? How is this all possible? Well, to answer that, you can look at this figure right here, where it shows a typical developing child. And they have a normal amount of connections in the brain. Whereas when you look at a child with autism, they have an abundant amount of connections that are going to completely different parts of the brain. So for instance, a kid may have tons of connections going on one part, but lack another. So some kids may have very high grades in mathematics. They may soar above a typical child in mathematics, but they may not be able to even say hello to them. And that just shows the difference in connections among the brain. On the far diagram, you'll actually see the firing of the neurons through the brain, showing that the non-autistic typical child has a much more concrete, distinct branching, whereas the autistic child is much more scattered and firing throughout the brain. So why is this all important? Well, it's important because the behavioral deficits that are going on with ASD is increasing dramatically throughout our lives. Over the past couple of years, there has been a huge amount of increase in numbers of ASD individuals. And many don't know why this is happening. They don't know if it's technology-based. They don't know if there's just more numbers. But they do not sexually reproduce normally. So something's happening that's causing this increase. So to properly understand the behavioral deficits that are going on to create a different therapeutic approach, one must backtrack the behaviors and understand the neural circuitry of what is going on. So in this experiment, we hypothesized that normal zebrafish will be able to adapt and act like normal individuals can to different environments, whereas autistic zebrafish models will exhibit similar behavior phenotypes to autistic individuals. So we have 3 predictions, 1 prediction for each stimulus: the social stimulus, the tactile stimulus, and the olfactory stimulus. All 3 of these predictions, we predict that the zebrafish will be able to adapt to the stimulus exposed, and they'll be able to regain their normal behavior. And the normal behavior of the zebrafish larvae is to circle the outside of the well, which you will see shortly. The zebrafish larvae is a good model organisms because they share a distinct amount of homology to mammalian animals. They have similar brain function, structure, and they also share the different senses such as vision, taste, tactile balance, olfactory, and sensory pathways. So many are asking, how can you make autistic zebrafish? Autistic zebrafish are made by taking away top 3 beta. So as you can see in figure A, top 3 beta is present, which shows distinct neuron branching, allowing the proper connections to be made to send signals to your body, such as walking. Whereas top 3 beta is removed in B and C. This shows a reduced amount of proper branching. It's not as distinct and it's more scattered, showing that they can't actually create those proper connections. So in this picture, you'll see that the normal control larvae on the left-hand side has top 3 beta present. And you can see their normal behavior are going in big circles in the outside of the well. They're able to explore the boundary. Whereas autistic treated larvae are not able to do that. They stay in one corner of the well because they are hyper-responsive. They do not want to migrate. They don't want to try a new environment. So they will actually create a very repetitive behavior of circling in one corner of the well. So this is our plate setup. This plate setup is our current plate setup. We have worked on this for 4 years, and after 4 plate setups, we finally created this one. This one has 3 zones, and they're all separated by a plastic barrier so that it's translucent so the fish can actually see through it. It has 2 holes in the outer well right here and here, and it has pores in the inner wall so things can be diffused through. The different stimulus are seen in this diagram, which shows the olfactory stimulus where a dead zebrafish head is placed in the outer zone. The social stimulus shows 2 social zebrafish placed in the inner zone, but of course the pores in the inner zone are not big enough for them to be able to migrate out. So they're stuck there. So this just allows the zebrafish to move into the well or out of the zone. The third stimulus is the tactile stimulus, which shows the brine shrimp. And the brine shrimp are actually able to diffuse out of the inner zone into the middle zone to create that chaotic tactile stimulus. So in this experiment, we used Daniel Vision and EthoVision software. We had a 6-well plate experiment set up, and they had used a white light routine of 30 minutes of light and 30 minutes of dark. This was repeated for 35 fish for each treatment and control. The olfactory stimulus from this experiment shows that the control group had a large amount of time spent and distance moved in the outer zone compared to the middle, whereas the velocity did not show any significant difference at all between the outer and middle, that it stayed the same speed. The treatment group also showed a very similar result, showing that there's a lot more time and distance moved in the outer zone compared to the middle. This shows that our prediction was correct, that the baseline data is observed and that the fishes are able to adapt to the stimulus. The olfactory stimulus heat map does show something interesting though, because this is the zebrafish head up here, and you actually see that the zebrafish that we placed in the well wanted to stay away from the olfactory stimulus. So even though it did stay in the outer zone, it actually wanted to move away from that for the majority of the time. The tactile stimulus showed that the control group, once again, had more time spent out in the middle, in the outer zone compared to the middle. And the treatment also displayed the same thing, where the tactile stimulus, the zebrafish did not want to be in the middle well. And this is mainly because you predict that they want to maintain their normal behavior. So you do not see a significant difference between control and treatment because they were able to adapt. This is the baseline behavior that we are predicting. The tactile stimulus shows a very equally distributed distance and duration in the outer zone, whereas the middle zone did not show that. This could possibly be due to the chaotic stimulus actually disrupting their movement a little bit in the middle zone, that they weren't equally distributed because they're like, hey, this is kind of crazy. Let me go back out to the outer zone. But you do see the similar pattern that they were equally distributed, circling the outside of the well, and that they wanted to be in this well, exploring the boundaries. Okay, so the social stimulus, last stimulus, shows that, once again, the baseline behavior was met. You see a big significant difference from the outer to middle in the control group, and you see another big significant difference in the outer to middle in the treatment group, showing that the zebrafish were able to adapt to the social stimulus, and they went back to normal behavior. The social stimulus shows a little bit of a different graph, the heat map, than the other two stimulus, and that is because you see a more equal distribution in the outer and the middle zones. And this is because they probably were just exploring their habitats, doing their normal behaviors, and they weren't bothered by the two in the middle. It wasn't a big stimulus for them to really react to. So all in all, you can see that treatment for ASD patients is very crucially needed. ASD individuals need to start treatment at a young age because as you all get older, your neuroplasticity will decrease. So to have a behavioral assay that's fully developed like this to treat ASD is very much needed. It allows one to see what will modify the zebrafish's behavior to potentially be able to translate over to humans. So once again, to test the future direction of this experiment would be to test this on autistic zebrafish larvae, where the top 3 beta gene is missing. This will allow one to see if their behavior is different than the normal zebrafish. Will the autistic zebrafish have a different behavior exhibited than the normal baseline that we collected in this experiment? And if they do have a different behavior, it will then be tested to see if there's chemicals that can modify those behaviors, if different learning treatments can be placed, such as after 5 days, will they exhibit the same behavior or will it be different? And these can eventually be tested, changed over to human applications. So in future experiments, we expect that this autistic social stimulus with autistic zebrafish larvae will show increased distance in the outer zone. And this is because when they experience the hyper responsiveness to the social stimulus. So they're not going to want to interact because they lose the interest in that social stimulus. They don't want to approach it. They don't want to explore that social stimulus. So they're going to stay in the outer zone of the well. Whereas the tactile stimulus also displays increased duration in the outer zone, but they're going to have the hyper response. they're going to get chaotic stimulus from the brine shrimp, and they're not going to want to be near it because they're going to get super overwhelmed like the shower. So they're going to want to get far away from that, and that's why they're going to be in the outer zone more of the time. The autistic olfactory stimulus, we're actually going to see something completely opposite than the other two, we predict, because they actually will want to move away from the olfactory stimulus in the top of the outer well and move into the middle well, because so once again, they're going to get overwhelmed by that stimulus, so they're going to become very hyper-responsiveness. They're going to want to move away. I would like to say thank you to Georgia Southern University's Honors Program and their Biology Department, as well as Chandler Scholarship Program, Dr. B and Jen Taylor, who's a behavior analysis that works with me. Any questions? Yes.
Okay, so on the, it was a long time ago, but it showed the normal behavior of the zebrafish circling and how the autistic ones stay in one corner. But what was the one on the bottom left? Where
That is the normal zebrafish, but that's just for a smaller time period. So as they were able to, as time went on, they would go towards the outside and continue that path. Yes.
So the top 3 beta gene in zebrafish causes more connections in the dendrites and neurons and stuff like that.
It causes disruption of connections.
Yeah.
Yes, so it's not more connections in the zebrafish, it's a disruption, so it's not able to properly fire. So that's why you see them not able to migrate and move around the well.
Is there a similar gene in humans?
There is a lot of similar genes in humans, and a couple of them actually have been transjected to be causing autism. But once again, since their brain is so tricky, nothing has been clearly determined yet.
I think it was the slide with the social stimulus.
Yes.
But,
This one?
sorry, one more. Yes. Is that where the hole is in the inner well? Like where that increased interest spot is? Or?
The actual holes in the inner well, they're little pores right here, 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 and here.
Okay.
So, and once again, most likely, because the brine shrimp are very small, I don't know if you guys have ever seen brine shrimp, so they're able to diffuse pretty quickly and very fast. So most likely, the brine shrimp came out, and it's just they didn't want to keep moving through it, so they stayed there and then went out as soon as possible.
Yeah. Do we know if in nature, if other animals such as zebrafish get autism naturally?
I don't think we actually know of any animals that get autism naturally, and that's why it's so interesting with the different speculations of what's causing autism. All the different autisms that are in animals are actually mutations that have been caused. So there is something going on with humans that are mutating them in the way to create ASD individuals. That's it? Okay.
Go ahead. Sorry. Did you use brine shrimp adults or not?
Sorry, what did you say?
Did you use brine shrimp adults or not?
We used adults.